get started. I think so this week is actually our final week, so a lot of students may not join this live version, but we record this our online, so other students and other folks can see that later if it's okay.
Okay, that's fine.
Okay, so let me introduce you and then we can get started. I'm super excited. So hello everyone, welcome to AI4H webinar number 21. And so today, I'm Jimmy Sun, the host for this webinar. And today I'm thrilled to welcome Dr. Irene Lee. In fact, I believe Dr. Lee is our very first MD and medical doctor speaker at this AI4H webinar series. And we did the 20 practice run until we invited a real doctor to come to this webinar. And Dr. Lee is not only a practicing retina specialist, but also a leading AI expert. He is a professor of ophthalmology at the University of Washington and also hosts the C. Dan and Irene Hunter Professorship. And Dr. Lee's work bridged the clinical care and also AI innovation, and especially in medical imaging. And he leads the NIH-funded AI4READI project, which he will talk about today. And I'm super excited because it generated some of the largest multimodal dataset for diabetic research. And his research focused on combining retinal imaging, EHR data, genomics data, and to advance AI application in medicine. I would say this is especially fitting to have him here because as far as I remember, retinal imaging was one of the early breakthrough use cases for deep learning in healthcare. And I think pioneered by some team from Google, and Dr. Lee has been really at the forefront of this field of medical AI. So without further ado, join me, welcome Dr. Irene Lee.
All right. Well, thank you so much for that warm introduction, and I'm excited to share with you all, the work that we've been doing in this Bridge2AI project from the NIH. So let me share my screen here. Can you all see that?
Yes.
Yes. Okay, wonderful. Okay. All right, so let me tell you about this project called AI-READI. It's really focused on type 2 diabetes as a model disease, and we'll go into more about why that is. So this is the rough outline for my talk. I'm going to start by talking a bit about big data and AI, and then about the NIH Bridge2AI program and what they're trying to achieve, and then a portion of that project, that effort, and some of the future directions. So as you all probably know, we are at this really interesting intersection in time where, there are very large collated data sets, and we have really advanced analytic methods for analyzing and harnessing that data. And if you had to do some crazy Venn diagram of how these things sort of relate to each other, in my opinion, that these are all sort of subsets of each other within AI. But data science has been thrown around fairly loosely and is not as well defined. And big data sort of sits in between here, where you need some of these as an inner ingredient to do some of the more interesting deep learning and machine learning work. And all of you probably know this, but there are, in image processing, there are many ways that you can phrase these problems, the holy grail of which is probably instance segmentation, where every pixel in the picture has been assigned a class, and you can tell apart two cats that are right next to each other as two separate instances of the same class. There's unsupervised learning, where we really have no idea what the right answer is. And one of my favorite examples of this is a image generator that learned the latent connection between horses and zebras, and can take a picture of a horse and turn it into a zebra and put stripes on it, but also change the context of the background to reflect, the context in which zebras are found. So that's really cool. And then, more recently with self-supervised learning, we have these, quote unquote, foundation models that can really leverage, information that is from pictures, just from it being in the foreground, being able to pull them out with the multi-headed attention heads in these models. So it's become sort of very clear that this these methods in deep learning can organize information de novo. And hopefully, as a I'm cognizant of the fact that I'm the first MD and clinician attending your seminar series. But in many ways, we want to go beyond what humans understand about medical diseases. And in order to do that, you shouldn't have clinicians saying, "I think this is a picture of X," because basically, if you train a model to recapitulate that, you're never going to learn anything new from human diseases. So, there's this critical gap that they noticed. And one of the biggest problems that they realized was that the data that was available for doing machine learning and deep learning were potentially biased. They came from, usually retrospectively collected, routinely available data sets that were sitting around on, hard drives and SANs and things like that for analysis. Then, some of these larger data collection efforts like the UK Biobank were heavily biased towards, healthy white British people and didn't represent the full diversity of human diseases. And so they realized that we lacked high quality, large data sets for doing machine learning. And so they started this program called Bridge2AI. And the idea was that it was really focused on this first part of the life cycle of training deep learning models. And that's the data preparation phase. This is the part that, people like doing the least, because it's sort of like the janitorial work that you have to do to clean the data, to get it ready to train the models. It's the least fun part of data science or machine learning, but it's often the most important, the most time consuming, and the most areas where the greatest issues of the downstream models come from. And so the Bridge2AI program was really focused on this first part. Within the program, there are 3 pillars that they've identified. And there's the data pillar for actually getting the data, diverse enough, having it be fair, and then be AI ready. Being ethically sourced, and then the people elements of all the people, both in training as well as collecting the data. And the way that the program is structured is that there's a center that oversees everything, and that's called the Bridge Center. They're in charge of kind of integrating what the data generation projects are doing. And then you have the 4 data generation projects within that. And so I want to go over these because you may find what we're doing interesting, but you may also find some of these other data sets to be really interesting and hopefully something that you'd want to dig your teeth into. So the first is called functional genomics, or cell maps for AI. And what they're trying to do is map out the cellular architecture across the human body and across different diseases. And they've made a lot of their data already available in many public data sets. There's this really cool idea of how the voice might be a biomarker of health, and that the way that you speak may be indicative of your risk of developing Parkinson's disease or having a stroke. And so they're trying to collect voice samples in a large enough population and tied with many different health factors to see if people can train models and do that kind of analytics. There's our project called AI-READI, and I'll go into more detail about what we're doing there, so I'll skip it for now. And the final data set called Chorus, that's focused on critical care data sets. So data sets that are generated from all the monitors that are present inside of the intensive care unit, how that might be harnessed to be able to predict who might be at risk of mortality or readmission after discharge. And so what's really, important, and what I want to stress here, is that these 4 data generation projects are vastly different from one another, and they really scale from, very basic science, subcellular type data, all the way up to data from the whole human body. And they're focusing on very different areas within biomedical sciences. The idea here is that if we work together and we solve problems about data cleaning, data generation across these things, and we learn patterns of how we do that, we can share that blueprint with the wider world, and they'll have an easier time collecting data at scale. So our project is called AI-READI. It's the sole purpose of this is basically stated here. Our goal is to create a multidimensional ethically sourced data sets in people for studying salutogenesis in type 2 diabetes. This is our website and QR code if you want to see what it looks like. You may have understood most of the words in that sentence, except for possibly the word salutogenesis. And the term salutogenesis is easy to think about if you understand what pathogenesis is. So pathogenesis is, the process in which you develop diseases, and salutogenesis is basically the opposite of that. And how do we encourage people to go back to a healthy state? We spend a lot of time in biomedical sciences studying this, about how to slow this down or halt it. We lack data sets that will help us bring us back to a healthier state. And so that's the term salutogenesis. to sort of tackle this idea of like, how do we collect a data set that can study salutogenesis? We borrowed this idea from the sort of the amazing advances that have happened in single-cell RNA-seq. So if you think about what happens in a data set from single-cell RNA-seq, you have each cell generates a transcriptome, and that transcriptome then is, put into a dimension reduction, usually something like a UMAP method, and it generates these sort of one-dimensional manifolds that on one axis will be quote-unquote pseudotime, where you can see the sort of a smooth transition of the cell going from a embryonic stage all the way to a terminally differentiated stage. And these map out to different, cell lines. And so what we were hoping to do is to scale this up to study it in a model disease. And so what we're hoping to do is basically collect a large enough data set with important key modalities of data, so that if we do a dimension reduction, one participant will be clustered here, and very similar people along very similar health states will cluster together and hopefully form these one-dimensional manifolds. And then one direction on here will be salutogenesis, and the other direction would be pathogenesis. So this is our idea. So we're trying to collect a large enough data set of many different modalities spanning from, really head to toe, to be able to hopefully downstream do this sort of embedding in a latent space that would help us understand salutogenesis. So this is our study design. We have 3 recruitment sites. So one is here at University of Washington, one is at University of California, San Diego, and one is at University of Alabama at Birmingham. Our goal is to get to about 4,000 people. I want them to be balanced in 3 different ways. One is with regard to race and ethnicity, one is with regard to sex, and then finally, most importantly, is the equal distribution across different health states. We want to make sure that we have equal representation here, because often, in data sets, it's very biased toward one way or another. But more importantly, for the dimension reduction to work, you want one of the main sources of variances to be, the disease state that you're trying to study. So just to give you an idea of like the kinds of data that we're collecting, I wasn't kidding when we said, I was saying it was from head to toe. We have data that, come from the eye and cognitive function testing from the brain, but we actually also ask people to take off their shoes and check the peripheral sensory component of the long, peripheral nerves that go along the central nervous system. And so to give you an idea of the protocol of what we're asking each one of these 4,000 people to do, there is a pre-visit phase where we ask them to go through all of these surveys, and it has many, many different things regarding, their diabetes and their diet and their smoking history, etc. And then they come on site for about 3 to 4 hours, and we ask them many, many things. So we get a very accurate current medication list. We do that monofilament test on the bottom of their feet, like that I was talking about. We collect their blood and do all these different markers that are really important for diabetes. And then we check their visual function, their cognitive function. We get many different forms of retinal imaging. We collect a 12-lead EKG, and then we bank their blood for future studies. What's a really kind of cool aspect of the study is what happens afterwards. So afterwards, we send them home with 3 devices. One is a continuous glucose monitoring device that sits, to measure their glucose every minute or so. We have a Garmin fitness tracker that we use to collect their activity. And then we built a custom environmental sensor to measure things with regard to the quality of air inside of their homes that they're breathing most of the time. And we'll go into sort of more about each of these later on. So, if you're curious, if you're not familiar with the ocular imaging, we are collecting a whole range of battery of retinal imaging. One of the really important things that happen with deep learning is not only the advances and the FDA approvals, but unfortunately, those FDA approvals are tied to a single device. And so this is one of the problems with, the state of the art with some of the convolutional models and even transformers, is that they are very sensitive to the noise that is present inside of some of these camera systems. And so they fail when you try to generalize to a new camera system. And so to kind of overcome that limitation, we're trying to create like a Rosetta Stone in this project where the same people are getting images across all of these different modalities, as well as scanning protocols within that, so that we have about 44 scans per patient. So in November, we released our data set. So one of the things that we're required to do by the NIH is release the data set as we collect it. And so the November data set that is available on our website is about 1,067 participants. You know, we have many millions of measurements with regard to their wearable devices and many different forms of imaging. And it ends up being about 2 terabytes of data. And we have about 7,500 biospecimens cryogenically at UAB. And so as of, a couple of days ago, we've had 490 research organizations that have downloaded this data set and have started to use it. And so really quite excited about what people will be able to discover using the data set that we've created. If you want to access this data set, you can go to our website, AI-READI.org, and then click this button. If you click this button, it'll take you to this website called fairhub.io that we've created. And the idea behind fairhub.io is that hopefully there's more people who generate data sets like this one, and that we will be able to showcase them here and provide, an authentication platform for them. And so right now, of course, we only have one data set on there, and that's our data set, but we're hoping that there will be more in the future. We have a marker paper in Nature Metabolism that was recently published. So one of the things that we had to really struggle through was how do we get, all this data shared with people in an ethical way? Because, people have released small versions of each of these modalities, but nobody's released a very large data set with all these modalities before in such a free and open way. And so we took this Swiss cheese model for open data sharing. And the idea is that each one of these barriers might mitigate some of the risk, and so that we can protect participants' privacy, but still be able to share the data. And so one of the things that we have as a very, front barrier to this is something called CI login that uses an EDU common federation to see if you belong to an institution, and that allows us to be able to kind of move forward. We created a brand new license. So this is something like, BSD or MIT or Apache licenses, but it's really meant for biomedical data sets. And so there's a couple things in here that, are very unique. It explicitly prohibits re-identification of study participants. It prohibits the distributions of models that are intentionally meant to copy or memorize the data. It prohibits the distribution of data beyond our data dissemination platform, and then allows for commercial use of the data set. We have this attestation, so we believe the license agreement will help with, commercial companies or institutions. But we realize that individual PIs and people don't really read the legal license very carefully. And so we actually have these statements that you have to type out character for character, and you can't miss a period or space. And the idea is that you're forcing them to read those sentences and type them out, and it creates a social contract with that person that they will attest to doing some of these things that will protect people's privacy. One of the other really unique things is that we created a watermarking system. So we have a system that goes through and actually creates an individually watermarked version of the data set as after you get approved. So if you make it through our process, then it spins up a job in the background that runs in Azure, and it'll generate a watermarked version of that data set, which then becomes tied to your identity. And so if this data set somehow appears online, we have the ability to track it back to that person who violated these terms. And so the other thing is that actually in our consent, we try to be very open about what could happen in the future. That as of today, we believe this data set can be freely shared, but future technologies may make it possible for people to link this information. And we have these barriers sort of in place to help protect participants' privacy. So this is clearly outdated, but one of the things that we did in April of 2024, so last year, is we released our pilot data that only had 200 some participants in it. And then in November, we released 1,067. And as soon as we did that, we saw this huge spike in the number of people trying to download the data set, as well as the amount of data that was transferred. We spent a lot of time building out documentation. So as a data scientist myself, I get really annoyed when I can't find documentation with how to use a data set. And so we built out a documentation website that really tries to go into this And one of the things that we did here was to try and get people up to speed on some of these domain knowledge that you need to know to be able to analyze these things. So if you've never worked with retinal images before, we have an entire section on how to do that. We also go into, the data usage with the license that we created that I mentioned. And then we ask people to cite this paper, which is basically our marker paper so that we can track at least who's using our data set. This is really the only way that we have available to that. We don't ask for you to put, our names on your author line or acknowledge us in the paper. We just ask that somewhere in your paper, you have this citation so that we know who's using our data set. We have some training resources. If you've never done any kind of ethics training for research in biomedical sciences, then we provide some resources to do that. And then we have a artifact called the health sheet for health data sets, and we followed that artifact template to answer the questions so people understand what the data set is for. These are the different domains that I was mentioning, where we list out how to use each of those domains and what the overview is, and we provide lots of different examples of how that each variable is actually being used with a description. I created this visualization using D3. This is a way to kind of visualize, the 1067 that we have. It is roughly balanced across this. We're missing some insulin group right now. The size of the dots are determined by the age of the participant, and you can see that they're roughly balanced across the different groups of diabetes. We have the 3 sites, and you can see that they're, again, roughly balanced across these 3 different clinical sites. And then most importantly, we provided recommendation splits. So if you want to use the data set, this is the data set you should use for training, validation, and tests, so that we can compare results across different papers. And one of the comments I often get is do you actually have all this data on all these people? And the answer is yes. Except for FLIO, where the machine was broken at certain times of our data collection, almost all the other modalities, we actually have full data for all these 1,067 participants. So I want to spend a bit of time talking about, some potential applications for using this data set. Just to be clear, we haven't published any of this. These are just sort of first level things that we discovered as we were doing the data cleaning and getting it ready for release. And one of the big topics in diabetes right now is studying diabetes heterogeneity. And so this is the work of Aya in our group. This is just a histogram of the different ages in our data set. And then if you look at the blood glucose that was measured from the that 3-hour time period when they came in to the clinic, you can see a wide range here. Some of these blood glucose levels is very, very high. We also have their hemoglobin A1C, and we can see that there is some spread here as well. This is a measure of their diabetes severity score, and you can see that there is a spread to work with as well. The continuous glucose measuring device is really cool because it shows you, basically every 5 minutes, what their blood glucose is for a 10-day span. And one of the measures that you can look at is the time that they've spent in range of reasonable physiologic levels of glucose. And so if that time in range is, 100%, that would be all the way up to the right. So the people without diabetes actually are sitting at, more than 80% in that time in range. If you have pre-diabetes, you can already start to see some of this creep over. And then if you're medication controlled, you see a lot more signal. And then if you end up being insulin controlled, you see that, you see a really wide distribution here compared to the other groups. If you do time in tight range, you can see even clearer shifts in the distribution. So this is a much tighter, more stringent glucose range, and this is really, really neat to be able to see this. And just to be clear, that these 4 groups is self-reported. So these are people who believe that they have no diabetes, or that they're pre-diabetic, or they're medication controlled. And we can see that there's some people who have no diabetes or pre-diabetes that may actually have diabetes, and they just do not know it yet. So this is a time series data set. And so one of the things you can do is you can plot the time series and see what those glucose levels look like across the 10 days. And you can see that there is, a wide range of spread. And if you generate sort of a time series thing where each line here is one participant, and you plot it, in sort of as a movie, you can see the individual trajectories and see the variance that is present in the data set. And you can see that some of these people have huge ranges in their blood glucose level across the 10 days. There's some really exciting stuff about uncovering new biomarkers of type 2 diabetes. And we have this custom-built environmental sensor that we built in our lab that measures, a whole bunch of different things that are present in the home environment every 15 seconds. So it measures their particulate counts at PM1, 2.5, 4, and 10. Obviously the temperature and humidity, but also the VOCs and nitric oxides. And then we actually have a multispectral light sensor on the device as well that measures the amount of blue shift light that is present in their house or natural light. This is what the sensor looks like. It was built out of a clear case so that people could actually see inside of it and see, what the components are. Over here is actually the air quality sensor, the light spectrum sensors here, and this is a touch screen so that people can see what is being measured. It was designed so that there's a 3D printed tray as well as laser cut acrylic that snaps together. And it's really cool. Like if you look at the spectrum, the light spectrometer data, you can see them sort of varying across time as the sunlight comes in and out. But you can also see very clear step functions when the artificial light turns on in somebody's house, and you can probably back out like what exactly is the temperature, or even if it's an incandescent versus like a halogen or fluorescent type light based on the spectrometer data. We are, there's been a lot of work in biomedicals, data science to study, PM levels with different diseases. And one of the critical, Achilles heel of that type of work is that they've had to map the environment of an entire zip code from data from like the EPA to the exposure of what people have. But in actuality, like if you look at individual people's exposomes of two people living in the same zip code, they could have vastly different profiles of the air they're actually breathing in their homes when they're sleeping at night. And so this is, participant A here versus B, and they're living in the same, city and even the same zip code. And you can see that there's a very different profile in terms of the particulate matter that is present. If you just take the mean of the PM 2.5 and you plot, the self-reported diabetes status, we were shocked to discover that there's actually an association here that's never actually been reported. So somebody needs to go and do a formal analysis here and publish a paper. Because it's very exciting to be able to see that kind of relationship and association between what you're breathing or what is in the air and your diabetes status. So volatile gas as well is less of a effect compared to the PM 2.5. And so, one of the things that as an ophthalmologist and a retina specialist, I'm always really excited about is this idea that the eye is actually a real-time view into the rest of the human body. The vessels that you see here are the retinal vessels, but these are the same exact kind of vessels that are present inside of your heart and your kidneys and your brain. And then the retina itself is actually part of the brain. It's an anterior extension of the same central nervous system that is present there. So if you can understand what's going on in the retina, you probably have a pretty good idea of what's happening in the brain. You have a much harder time of understanding what's happening in the brain without, cracking it open and trying to take a sample of it. So if you're not familiar with retinal imaging, we have many different kinds. So the one that I showed you before was a color photo. This is an infrared reflectance photo, and then this is a modality called optical coherence tomography, or OCT. And then you can think of it as sort of a CT scan of the retina. It's a volumetric imaging of the retina. So we have, this many different forms. So we have color, like two-dimensional imaging, as well as this three-dimensional imaging in grayscale from the OCT. And the OCT is kind of a remarkable technology in that it provides a non-invasive, very quick view into somebody's retina at a resolution that is almost at the scale of what we can see in histology. And so these layers actually correspond directly to these bands that you see on the left-hand side that we can measure without, taking somebody's retina out. We can measure it very, very quickly in the clinic. There's a newer technology called OCT angiography, and it turns out that if you take the same OCT image over and over and over in the same exact location, you can look at the variance in the phase and intensity, and then understand what the flow is happening in each anatomic location, and then actually get out a perfusion map of the retina. And it's really amazing, the detail that you can see across different severities of diabetes in the retina. As you can clearly see, there's areas here that the blood vessels are missing, and there's not enough nutrients coming into the retina there. There's a very new and more like a research imaging device that we have in our data set. And it's based off this fluorescence lifetime. So if you shine, a stimulus at the retina, and then you capture in picoseconds the photons that are being sent back at a different fluorescence channel, and you can look at the decay of the photons per picosecond over time and understand sort of the fluorescence lifetime of the compounds in that location of the retina. And so there's this newer modality called fluorescence lifetime imaging ophthalmoscopy that was only that it actually is not available commercially. It's only available in the research context. But we actually have it in this data set. And it's the first sort of large scale data set that has this modality inside of it. We have two different frequencies that we're measuring the spectrums of, and you can sort of see these different patterns. Nobody knows what to make of these patterns yet because it's such a new device, and that's where some of the machine learning, we hope that people do, some exciting machine learning to be able to analyze this data. So, if you want to sort of understand the scale of data that we're collecting here, we have color images of very different modalities. So this is a instrument that costs maybe $500, $600 that is portable, that you can take into a third world country, and it generates an image that looks like this. And then on the other scale of that, we have a very expensive camera systems that cost like hundreds of thousands of dollars that gives you an image that looks like this. And what we're hoping that people will do is generate ground truth labels based on the high quality imaging, and then train models that can work with this portable device, and then hopefully be able to deploy them at scale in third world countries. I mentioned OCT and OCTA as different modalities that we have in our data set. We also have inexpensive machines as well as high quality machines that span that spectrum as well. And we have a series of different kinds of OCT machines as well. So this is a swept source OCT device, as well as spectral domain OCT devices. And again, one of our hopes is that this will create a data set that is large and diverse enough for people to kind of build models that work everywhere instead of being tied to a single machine. This is that FLIO, fluorescence lifetime imaging device that we've come up with sort of a way to visualize this data that doesn't, that uses some of the dimension reduction techniques to do it. And so, where's this all heading? This was, one of the really cool papers at the beginning of the era of deep learning and retinal imaging that was published in Nature Biomedical Engineering by the Google group, where they showed that you could predict, a whole bunch of different cardiovascular risk factors from retinal images. And this was a shock that, to the world, that you could actually predict whether somebody was a smoker based on, their retinal imaging with a deep learning model and their age, as well as their hemoglobin A1C and their BMI. This one in particular shocked the ophthalmology world because we've been staring at people's retinas since, the dawn of our profession. And we didn't know that you could actually predict somebody's sex from a retinal image. This is, some work that shows that even dynamic things like blood pressure could be predicted fairly accurately. This is work that our lab did in collaboration with Pierce Keen's group in London, where we published this paper in Nature about foundation models for retinal imaging. And what we're hoping that people will do is that, using these newer generation of deep learning models, that they'll be able to kind of use this as a starting point for training some of these more difficult tasks, like predicting, different systemic factors from a retinal image. They showed here that, even with an OCT or a color fundus picture, you could predict whether somebody has a heart attack or heart failure and so on. And so this whole field is now called oculomics. The idea is that with pictures of people's eyes, we can understand the rest of their human body. This is, one of the more exciting things, in my opinion, that came out of that paper and that work is that we are able to show that, with much less data, you can actually achieve very reasonable things for performance-wise for these deep learning models using RetFound as a foundation model for for starting the training. This is our marker paper that I mentioned earlier on. It's available at Nature Metabolism. And, I don't put too much weight into these, altimetrics, but it was exciting to sort of see that there was a lot of interest from, the news media outlets as well as social media about this data set. We've since published a couple other papers. One is on this, on the actual protocol that we're using. So if you ever wanted to replicate what we were doing in our data collection, you can read this paper. We have our manual of operations available there. And then we've been working with the Bridge2AI consortium on this paper about what it means to be AI ready for biomedical data. Some of the things we're working on now, we're in our third year, to be clear. And this is a 4-year project. So we only have till November of 2026 to finish everything that we're hoping to do. This year, we are creating a data access committee for some of the controlled elements of our data set. We're planning to do whole genome sequencing on all the samples we have so far, which should be around 2,500 or so. And then we anticipate releasing our year 3 data set in November or December of this year. So, some of the things that I'll say here is that, I think we're in a really exciting time. There's all sorts of things that are happening now with vision language models and multimodal models that are scaling up to be able to handle really complex input data and hopefully be able to find, latent disease associations that people have not been able to find using traditional, statistics. And I think it's very clear that, collaboration is really the key here. So no longer can you sort of collect your own little data set at your institution and train a deep learning model and hope to do something with it. It's very clear that you need very large data sets across many different axes of variance in order to train models that work in the real world. I'm the lead PI on this project with my wife, Cecilia. But we're both indebted to the very large team of PIs that are part of this project. And to be fair, I've only scratched one surface here. There's actually a whole other component with a training program that we've developed, as well as a software ETL pipeline that we're open sourcing, and all sorts of other parts of this project that you didn't have a chance to get into. This is our website, QR code again, if you're interested. And then this is my own lab at University of Washington that a lot of these folks have bent over backwards for creating this resource. So I'll stop here.
Thank you.
And I'm happy to if there are questions.
Thank you, Dr. Lee. This is amazing. So for the audience, if you have a question for Dr. Lee, please put them in the chat, or you can just ask directly. That's also fine. And I can maybe get started by asking you this data set that you guys are creating are very different. I mean, the data set that we are using in AI for healthcare, that's probably the most well-known one, is like this mimic data set from MIT, right? So I think in comparison, your data set is much richer and multimodal, much like different modality, and also kind of a collected for research purpose versus some secondary use of some emergency room type of data. So what's your so since you are the PI, you propose this project, what's your take on this two different direction, like just gathering as much real world data as possible in just like what Mimic does, right? They have this days maybe tens of thousands or maybe even hundreds of thousands of patients in that data set, versus in your case it's a few thousand, like a 4,000, but very very rich and carefully designed, like collected high quality data. So what's your take on like this two different approach?
I struggled with this, right? So like as a data scientist, or when we're sort of training deep learning models, we want lots of data. We're always wanting millions, if possible, of independent samples. And often we're sort of forced to use these retrospective, routinely collected data sets that are from regular clinical care as a way of training these models. And I've gotten into debates with people about, like, is it better to have thousands and thousands, if not millions, of that kind of data versus a highly curated data set like this. And I used to be in the former group who said, like, I don't care, I just want lots of data, and I'll figure it out. But I started to realize that that was probably a flawed way of thinking as I started to think about models that would be deployed in clinical use. And the reason for that is that if you have a data set that was very biased in its underlying population that it was drawing from, it's very likely that model will not generalize to a different set of people. The other thing I would say, though, is that like the real world variance that is present in that kind of data set is actually really important for training models that work everywhere in a way, right? So you want to capture some of that noise when you're training models. I think that this data set is not actually meant to train models that will work in the real world, to be clear. This data set is meant for discovery. And so in my mind, there's a way to use deep learning to train models to find new associations, to find new scientific discoveries, where you need to increase that signal to noise ratio as much as possible to find that. And in some of the noisy real world data sets, it can be very difficult to find that signal without having millions to sort of overcome that noise. So I think they sort of serve two different purposes, and they're both important. I wouldn't discount one being necessarily better than the other. In fact, you may need both to in the long run. So I realize that's sort of a long-winded answer to your question, but I think it's actually a very nuanced question.
Yeah, this is, thanks for your nuanced answer. I think this is actually quite important, right? You mentioned that this data set, the AI-READI data set you guys are curating, is for discovery. I had a thought on, the recent all this AI agents and AI kind of AI agent for scientific discovery. What's your thought? Do you think this those line of work? So, for example, a few weeks back, months back, we had James Sill from Stanford here talking about using those agents for scientific discovery. Do you think now you have curated a very high quality data that actually can enable discovery? Those AI agents can do this discovery faster. Do you think that's a promising direction for students or whoever to explore?
Yeah. I'm going to give an unpopular answer.
No, please go ahead.
So I've been thinking about this a lot, and I think agentic AI is a step in the right direction. It is where the field is moving, or has moved in outside of biomedical sciences. The AI world has basically shifted over to agentic frameworks, and I think it's very powerful. Don't get me wrong, but in many ways, I feel like the tech industry is pulling a fast one on the public in a way, because like when they call these multi-agents, it often is the exact same model under the hood, and they're just giving it different prompts so that it behaves differently. And it's not really like a specialized model that was tailored for one particular domain or task. It's really the same exact model, general purpose model, but different prompts that force it to behave differently. Or they spit out code that then gets executed. So I think that way of thinking is great. The current generation of agents probably isn't the future generation of agents. I think there are going to be a lot more specialized agents that will be paired up with like something like a vision language model or other things that can do really cool things. The biggest problem I have with this idea that they can do discovery or science like new ideas, right? Is that from my understanding and what I've noticed with large language models is that they're very, very good at interpolation. And a lot of what they're doing is basically interpolation under the hood. And so they're taking, one data point over here where there's something on the internet about that particular topic, and then different data point over here, and they're kind of bridging this gap and giving you an answer that's in between. And it's tailor fit to what you're asking, but it's really under the hood. It's connecting different dots. When you're talking about new discovery and new scientific directions, often it's an extrapolation task. You have to see where the current data sets are, and you have to see where there's data missing, and you have to be able to jump in that direction. And from what I've noticed, these models are not very good at that. At least the current generation of large language models don't seem to be very good at extrapolation type tasks. And so I think it's amazing. Deep research is amazing, right? Like it's able to really give you a really great answer to a scientific question where the answer exists. I think deep research may not be so great at answering a question where the answer does not exist, or is not some sort of combination of things that people have already understood or discovered, if that makes sense.
Yeah, I think that makes perfect sense. So a lot of those are, I guess, a human or good human scientists have those intuition or some kind of a creativity. Maybe you're arguing it's maybe this AI model may not have those intuition or creativity.
Well, so whereas creativity is a copy of one style to another that hasn't been done before, I think models can do that fine, right? Style transfer type things is done very well. But what I'm talking about is like a completely new line of thinking or completely new area of art or science or whatever it is. The models are not great at figuring that out like a human can do, at least today. That seems to be one of the limitations of the current generation.
Interesting. I think one of the audience, Yukon, was asking a question I had in mind as well. Like, based on what you're saying here, is there any, okay, I guess there's two questions, right? Is there any plan that genomic data also are downloadable? That's a very practical
Yeah.
question for the data set?
So we're not going to allow people to download people's whole genomes, right? Like that seems to be a violation of privacy. Um, what we are going to do is make it available for data use agreements. So if you sign a data use agreement with our institution, we would be able to share the whole genome sequencing with you. You'd be able to download it to your computers, but you'd have to undergo a data sharing agreement to do that, just to put more provisions in place about the use of that data set.
Okay, that makes sense. And the follow up question on the scientific discovery part, I had also that same question. If do you think the hallucination is kind of a creativity, or is that a because also kind of it's not right? Because a lot of those people, or I mean, researcher focusing on in the scientific world, right, trying to not hallucinate. Like, okay, we don't want to cite a paper.
Yeah. Usually
don't
hallucination is
exist.
a bad thing, right?
Right,
Like we're trying to get rid of it. But I guess the question is asking, is there some way to harness that those what we are calling mistakes as a way to solve this task? That's a really interesting idea. It's not something that I've thought very deeply about yet. The whole world has been focused on, how do we get rid of these hallucinations by using things like RAG frameworks and other things to do that. It is an interesting idea. It's like, is there a way to encourage hallucinations so that we end up being able to get these models to do these sort of what I've been calling extrapolation type tasks?
Interesting. So, I mean, in the next just last few minutes of this webinar, we usually ask our speaker to give advice for our computer science students who are interested in this AI for healthcare or medicine kind of topics. And you, I think, have worked with a lot of computer scientists and students and professors, right? And what's your maybe a couple of questions there. One is, what's your advice for those students who decided, okay, this is the direction I want to do? What kind of a strategy or things do you think are missing from some of those standard CS students are in like with machine learning background, right, if they want to get into this field?
Yeah, I think one of the hardest things I've noticed is that it's very hard for groups to like if there's these different collaboration models that I've seen over the years, right? So you have some clinician who thinks they have a great idea, but they don't understand computer science at all, and then they work with a computer science professor and their students to solve this problem. And what ends up happening, unfortunately, is that there's a big miscommunication that occurs where the clinician doesn't know how to state the problem in a way that a computer science professor or their students can understand it. And then the computer science people don't understand the medical domain side of it. And so they go and solve what they think is the problem, right? And they do that for like a year or months, and they come back to the clinician, and the clinician's like, that's great, but that was useless. That is not at all what I was asking.
Right.
And then there's this cycle that goes on, and after a while, it ends up being like the collaboration sort of breaks down, and it isn't able to move forward. The areas where I've seen the most successes is when there are people who are willing to bridge both worlds. So being able to find people who live at this intersection of medical sciences and computer sciences, and either become that person or be willing to find those people to bridge this gap, because it's the lack of communication that often I see being the biggest barrier for successful projects. It's not the willingness of either side. It's unfortunately just a gap in communication.
But do you think for computer science that the students should, for example, like take some medical classes and show up in clinics?
Well,
like
no. I don't think it needs to go that far. I think if there is a problem or project that you're working on, I would encourage the students to really dive into that domain, like try to understand it and the clinical applications of it. I don't think they need to go to medical school and learn the entire body of medical sciences. But at least for that modality or that particular problem, try to understand it from the clinician's perspective, what the problem they're trying to solve is. Because often that is the gap that occurs, is that, the students get like a big data set, and then they go and often solve what they think is an important problem, and that it doesn't always align with what is actually a problem in the real world. And so I think that's where, I'd encourage, your students to be a bit more proactive about trying to engage on the clinical side. I don't think they need to go shadow a clinician or anything like that, but at least for that problem that they're trying to solve, and that modality, try to actually understand how it's gathered, how it's actually used in the real world. And then think about, what are the relevant problems that can be solved using machine learning or data science.
So it's the same question for like advice for clinicians. Do you also encourage them to learn some AI or machine learning, do some Python coding today, or what's your suggestion for
Yeah.
those MD students?
So I've mentored a decent number of MD students in my lab, and I only take them if they're willing to learn how to program.
Okay.
And so, but that's me. Like I am a very particular kind of breed of person, and I want to create more people like me who are in the medical domain who understand computer science. And so that's my bent on things. The general advice I give to most clinicians is that it's not important for them to learn how to program, but it is important for them to understand the concepts, and understand the basics of machine learning, and what overfitting is, what underfitting is, like what the cursive dimensionality is, and like these basic things, so that they understand when they look at a data set or when they have a clinical problem where they think, oh, this is a perfect application of AI. It's often not a perfect application of AI because they have no idea what AI is, right? And so it's really important for them to understand and learn that. And so, but to answer your question, yeah, I do think these two worlds need to kind of come together a bit, in their willingness to understand each other, before we start to see sort of big advances occur.
Great. I think with that, and thank you, Dr. Lee, for the wonderful talk and the amazing data set. I think a lot of our audience will find useful and beneficial. You probably will see some spike in network volume.
Yeah,
Download.
we'd love to see that. We'd love to see that. Thank you.
Thank you. Thank you for your time, and see you. Bye.
Bye.